Hello students, today we will study organic chemistry, some basic principle and techniques in which we will cover NCERT section 8.7.8 and 8.7.9. This is disclaimer. Now, in this class, our objective would be to look upon the influence of electronic displacement on structure and reactivity of organic compounds. Now, we have already started with this objective and so far we have covered two topics, this inductive effect and resonance effect, right? Now, in our today's lecture, next focus will be on electromeric effect. Then the last one, which is hyperconjugation. So this were the four effects. So two of them were already covered. Today we will cover the remaining two. Apart from this theory part, we will also do some questions, which is in-text question 8.12 and 8.18. Let us start with the electromeric effect. Now, electromeric effect is a temporary electronic displacement and it operates through the pi electron system. So this is the only electronic displacement which is temporary in nature. Now here is an example to illustrate the same, that how this electromeric effect is temporary. You can see here how the electrons are displaced within the molecule. Now what are the key points? So first of all, you should remember that the curved arrows are representing the movement of electron pair. So this is the normal way to represent the movement of electron. Now, here you can also see that the electron is being donated from a pi bond onto a carbon because the tail of the arrow is on the pi bond and the head of the arrow is on the carbon. Next, why we are calling it as temporary effect? To understand this, you must notice one important thing here, that this movement of pi bond is only driven when there is a presence of an attacking reagent, and that is proton here. So basically, you need an external factor to drive the movement of electron. If this external factor is not present, the movement of electron that you are seeing right now will not be observed. Means the effect of electromeric is temporary because it is only operational in the presence of a attacking reagent. Now, once you remove this attacking reagent, the effect becomes completely reversible and the pi bonds move back to its original substituent. I hope you are getting my point. Now you may ask that the pi bond is moving on to the carbon. Why is the carbon not getting a negative charge? Because the H plus is being the one which is neutralizing this negative charge by attaching to the carbon rich in electrons, right? Whereas the other carbon is getting a positive charge because it is lacking one electron. Okay, so this is the reason the end product is not containing a carboanion. Then moving on to types of electromeric effect. Now we will see these effects and see how they influence the chemical reaction as well. So they can be of two types depending on the environment. The first one is positive electromeric effect. In this, we see that the movement of electron is in a specific direction during the reaction. Whereas during the minus E effect, the result is totally opposite. Let's start with the positive electromeric effect. Now, here the pi electron shift towards the attacking reagent. So it's very simple, right? So if your thing which is showing the electron movement, if it is moving its electron towards the attacking reagent, then we call that effect as positive electromeric effect. Now it is typically observed when the reagent which is present is an electrophile, means it is electron loving. So the previous example, if you consider, which is the addition of H plus to C double bond C, you can see here very clearly that the double bond is moving on to the carbon, and now that negative charge on carbon is being donated to the hydrogen ion. Why? Because H plus is a electrophile. because it is deficient in electron. So this is the most important point. So overall, what you can say, that due to the presence of this attacking reagent, your pi bond is donated onto the H plus ion. So it is an example of plus E effect or plus electromeric effect. Okay. So the reagent gets attached to that atom as a result of this, which receives the electron pair from the double bond. Now moving on to the next type of electromeric effect, we have now the negative electromeric effect. Here, the pi electron pair shifts away from the attacking reagent. And in this case, we will observe that the electron is being donated by the nucleophile, which is nucleus loving. So here is an example for that. Here, your Cn minus ion. Okay, so it is containing a negative charge. So it is a nucleophile. Therefore, it will donate electrons onto the doubly bonded carbon. As a result of that, the pi bond will move on to the next carbon and it will create a negative charge on that carbon, whereas the Cn will be attached onto one of the doubly bonded carbon. So this is the overall course of reaction or overall course of the electronic displacement. Now what you can observe here, that the attacking reagent is donating electron. So the overall double bond is accepting that electron pair. So it is showing a minus E effect. I hope you are getting my point. Means if your electron displacement is resulting in donation of electron to the attacking reagent, it is plus E effect. If it is resulting in acceptance of this electron, then we will call it as minus E effect. Now, plus E effect is shown by the attacking reagents which are electron loving or electrophile, whereas the negative electromeric effect is shown by the attacking reagent which is a nucleophile and it donates electron pair. So as a result of this, the attacking reagent attaches to the positively charged atom and hence neutralizes it and creates a carbon ion. So this was all about the electromeric effect. I hope you got the point. And why it was important? So I would say that in most of the reaction, you will see this electromeric effect operating. Okay. So as a result of this inductive effect and all, this movement is being, you can say, coursed through. And the next part is your electromeric effect. Now we will move on to the next electronic displacement, which is hyperconjugation. Now, hyperconjugation is the delocalization of sigma electron. Now, there is a very quick recap to all of the electronic displacement. If you consider the permanent one, so in the case of resonance, there was delocalization of pi electrons. Hyperconjugation is delocalization of sigma electron. And your inductive effect is movement of electron. So I would not say that their electron is being completely displaced from their position. It is being just polarized. So that is the basic difference between an inductive effect, okay, and other two effects. And the difference between hyperconjugation and resonance is what? In hyperconjugation, the sigma electron is shifting, and in the resonance, the pi electron is shifting. Now here, the sigma electrons of carbon is moving on to the p orbital of carbocation or alkene. So this is the example of that. We can see here that the electrons between the hydrogen and carbon. So that is the reason I have written CH. So the electrons between the carbon and hydrogen is being moved on to the p orbital. So this is the empty p orbital of a carbocation or an alkene. So both can be the reason of hyperconjugation. Okay. Either it can be a carbocation or it can be an alkene. So here we have a carbocation and the sigma bond of this CH bond is being moved on to the carbocation's empty p orbital, empty 2p orbital. Now, what are the key points that you should remember? First of all, it is also known as no bond resonance or Baker-Nathan effect. Second, it is permanent effect. Okay. Then it does not depend on any external factor. So this is the reason it is a permanent effect, because it is always operational, whether you apply any criteria or whether you remove any criteria. Then what is the condition for hyperconjugation? This is the most important one. Why we are saying that only the carbocation and the alkene are capable of showing this hyperconjugation. What is the reason behind it? So if we consider it for carbocation, then the alkyl group, which is containing sp3 hybridized carbon, if it is directly attached to the unshared p orbital, means of the carbocation, then and then only you will see the hyperconjugation in case of carbocation. Okay, because here the sigma electrons of the CH bond is being donated onto the empty p orbital of the carbocation. Then for alkene, what is the condition? Here the sp3 carbon should be directly attached to the unsaturated system. So here you can see an example of it. So we have a CH3 group, which is of course sp3 hybridized, and we have a doubly bonded carbon, which is sp2 hybridized. Now here the possibility of hyperconjugation is there. Okay, I hope you're getting my point. Now next we will see hyperconjugation in carbocation. How does it occur? Means how you will show it on the paper. So that is the most important part. You will never show the orbitals and all. Like our resonance, you will also need here a convenient way to show the hyperconjugation in case of carbocation. For example, if you consider an ethyl cation CH3CH2 plus, then electrons will move from the CH bond of CH3 and they will be delocalized onto the empty p orbital of the ethyl cation. So here is an example illustration of that. You can see here that the HA hydrogen is being donating electrons. Okay, and it is donating its sigma electrons onto the carbocation and hence making a double bond. Similar to that, HB can do the same thing and HC can do the same thing. So these three hyperconjugation structures are possible for the given carbocation. Got it? Easy to consider. So you can easily consider this. The sigma bond is moving. If you want, you can show this by arrow also. The tail of the arrow will be between C and HA, means the bond, and the head of the arrow will be between CC bond to show the movement from sigma to pi. So basically, your sigma bond is becoming a pi bond. Now next, this can help in stabilizing the carbocation. So this is the most important part. If you are seeing that more number of alkyl groups are on C+, then there will be greater number of hyperconjugation structures possible. And greater number of hyperconjugation means more will be the stability of carbocation. Now this is also seen in case of resonance. If you remember that more number of alkyl groups result in more number of resonating structure. So that would increase the stability of the carbocation. And what is the reason behind it? Can you think of the reason? Of course, you know that more number of alkyl groups increase the stability of your carbocation. But what is the reason of that? And what is the reason for hyperconjugation? Why these both effects are stabilizing? And to connect this, you can think it of in a simple way. So basically, your carbocation is something which is electron deficient. Means it is carrying a type of burden on it. But if you just delocalize this burden, rather than a single carbon, if you just spread it throughout the molecule, that will make the burden simple to carry. Or you can say it will make the carbocation stable. So you can just take your analogy from your daily life. So if there is a 10 kg mass, if two of your friends are present, one of these is carrying 5 kg each, then that will help you to carry that luggage easily. Okay. If you have 3 friends, then that would be even greater and even appreciable. So similar to that, more number of resonating structures or more number of hyperconjugation structure is kind of distributing the burden of electron deficiency onto the next carbons and hence stabilizing the structure. Now, if you consider this criteria, then we can easily say that the tertiary carbocation is the most stable one, then comes your secondary, then comes your primary. Now, this same trend is seen and this same stability is being induced with the inductive effect, if you remember. But the effect of hyperconjugation is more appreciable than the inductive effect. Means if something is stabilizing the hyperconjugation structure and the opposite stabilization is shown by the inductive effect, then you will consider stability according to hyperconjugation. So the most powerful among the hyperconjugation and inductive effect is hyperconjugation. You will remember this. Okay. Now suppose if you take resonance also in this picture, what will happen? So the resonance is the most powerful one. Then the next deciding factor is hyperconjugation, and the least, I would say, contributing factor is inductive effect. So if something is being stabilized by resonance effect, then that would be the most stable one. I hope you will remember this point. And most of the students do a mistake of ignoring this hyperconjugation, and they do mistake in their paper, right? So remember, the effect of hyperconjugation is very, very significant in comparison to inductive effect. Moving on the further, we will see hyperconjugation in case of alkenes. For example, if we take propene, then there will be delocalization of CH bond sigma electrons, and it will be delocalized onto the pi system of alkene. Here's an example of that. You can see here that the sigma bond between carbon and HC hydrogen is being moved on to the next bond, and that creates the movement of the pi bond onto the carbon, creating a negative charge onto the carbon. Similarly, that same can be done by the HA, that same can be done by the HB, and that same can be done by the HC. Now these three structures are hyperconjugation structure of the alkene. So they will be stabilizing the structure in a way. Now you can say that more is the number of hyperconjugation structure possible for a given alkene, more stable the alkene will be. Okay, so remember this point, it's very, very important for your examination. And you can just learn it as a mnemonic. So more number of alkyl groups on C+, more is the number of hyperconjugation, and also more is the stability of alkene. Now we will do some questions. So this is problem number 8.12. Giving justification, categorize the following molecule ions as nucleophiles and electrophiles. So you have HS minus, BF3, C2H5O minus, CH3 whole thrice N. Then you have Cl plus, CH3 single bond C, double bond O, where C is containing a positive charge. Then we have NH2 minus and N2O plus, NO2 plus. Let us move on to the solution. So how you will decide which one is nucleophile and which one is electrophile? If you consider the definition of nucleophile, then these are those species which love to go towards the nucleus. They are nucleus loving. That means either they will contain a negative charge or they will contain a lone pair. So this is the only way to make the substance electron rich. And if you consider these four species, so three of them are containing a negative charge, whereas the CH3 whole thrice N is containing a lone pair. So that is the reason it is a nucleophile. Okay, so this is the only two possible condition for a substance to be nucleophile. Now, the species have unshared pair of electron. So if they have a negative charge or a lone pair, you can say that they have an unshared pair of electron that can be donated. Now, they donate shared pair of electrons with an electrophile. So that is very obvious. If something is donating electron, means there should be a sink, and that sink is the one which is known as electrophile. Okay, so these are the four nucleophiles present in the given options. Then moving on to the electrophiles. If you remember the definition of electrophile, then these are those species which are electron loving. Here, BF3, Cl plus, CH3, CO plus, C plus O, NO2 plus. So out of these four are already containing a positive charge, whereas the BF3 is not containing any lone pair. So that is for sure that it is not a nucleophile. But how it is electrophile then? If you consider the octancy of this boron, then it is sextate. Okay, it is not having a complete octet. Therefore, it is electron deficient and hence it will act as an electrophile. Okay. So the reactive sites have only 6 valence electron and a positive charge on the central atom. And it will accept electron from a nucleophile. Moving on to the next question. Explain why the following two structures, 1 and 2, cannot be the major contributors to the real structure of CH3 C double bond O CH3. So these are the two resonating structures given, which are 1 and 2. You have to decide that why these two structures are not a major contributor. Now, how do you decide a major contributor? It's very simple. If it is not stable, then it will be not a major contributor. Starting with the structure number 1. So, if you look at the structure number 1, then the carbon atom is having an incomplete octet. And this is the key reason it will not be a major contributor. You can see onto the carbon, it is containing 6 carbons, 6 electrons, because it is a carbocation and an electron deficient species. Therefore, the structure number 1 will not be a major contributor to the original structure. Moving on to the next structure, which is structure number 2. So if you look onto the structure number 2, what you can notice that they involve charge separation, means the positive and negative charge are present far from each other. You can see here that we have a charge separation. One of the oxygen has a negative charge and one of the oxygen has a positive charge, and they are present at a large distance from each other. Due to this reason, you can say that this is not the major contributor. Now you will ask that how are we deciding it? On whose relation we are deciding it? So just draw the simple structure of this CH3 C double bond O OCH3. You will see that you can have a structure which will not have a charge, and that will be considered as the major contributor rather than these two which are charged at the same time. One of them is having an incomplete octet. I hope you're getting my point. Now let us summarize today's class. So we started with electromeric effect, which involves the temporary electronic displacement of molecule in a pi electron system. Then it can be of two types. If your substance is donating electrons onto the attacking reagent, it will show positive electromeric effect or plus E. And if it is accepting electron from an attacking reagent, then it will show a negative electromeric effect. After that, we studied about hyperconjugation, which is basically the delocalization of sigma electrons from sp3 of a CH bond to the p orbital of a carbocation or alkene. So this was all for today's class. Thank you for your attention.